So number 4, separate sheet of paper. I've talked a little bit, and it's now 7:48, just so we can give my extra minute there. So Johanna, I don't know if I'm saying that right or not, jogs along a straight path for 0 to 40. Johanna's velocity is given by the differentiable function. Selected values of v are up here. T is in minutes, v is in meters per minute, are given in the table above. So like distance equals velocity times time, sort of. A better way to say it is the integral of velocity would give us displacement. Use the data in the table to estimate the value v prime at 16. Okay, v prime at 16. So v prime is, well, if it's estimated, that's like change in v over change in t. But at time equals 16. So how am I going to do that? What values will I use to estimate at time 16? 20 and 12. So I can do v prime from 20 to 12. Now that's not going to be exact, but that's why it says estimate. In fact, it's as good as we can do. So v at 20 minus v at 12 over 20 minus 12. So 240 minus 200 over 20 minus 12. And this is no calculator, which means I should probably just leave that as my answer. I mean, it's not hard, but I can leave that and just go to the next problem. Like, that's an okay answer. Most people keep going just out of habit. It's also not difficult. I'm a little surprised it didn't ask for the units on that. Let's go ahead and do the units, because it asked for the units on the next one, but change in v over change in time. So the 240 and the 200 were meters per minute. 20 and 12 were minutes. So what is my units on 5? Meters per minute squared. That also kind of matches up with what else do we know is, what's another name for the derivative of velocity? Acceleration. So it makes sense that the derivative of velocity gets us an acceleration answer. Part B. Using correct units, explain the meaning of the definite integral 0 to 40 absolute value of 0 to 40. Or excuse me, 0 to 40 absolute value of v of t dt in the context of the problem, and then approximate it using a right Riemann sum for intervals and so on. Okay, we haven't done this. This is why I wanted to do, and we didn't get to it, the Cupid's Shuffle worksheet. Because in that Cupid Shuffle worksheet, you take a bunch of steps to the right, you take a bunch of steps to the left, and if you do it correctly, you're right back where you started the song. In fact, the place I got that worksheet from says that all of those like line dance moves, the net displacement is 0. You always end up where you started. Now, maybe be cursed with thinking about that the next time you're at a dance or a party and you're taking 3 steps to the right and 3 steps to the left and 2 steps forward and 2 steps back. Like, you travel a lot, but your displacement is 0. And in fact, that's the difference between these two things. Without absolute value bars, it's displacement. Right? Because this would just be your position at 40 minus your position at 0. And so you may have walked all the way around. Right? This is also the, if you run around the track 4 times, your displacement is 0. If absolute value bars are on there, That means we're not thinking about negative. Every step is a positive step. What do you think the word is that matches the absolute value bars? Distance. And so you run 4 times around the track, you've run a mile, you've gone nowhere. You do the Cupid shuffle, you've gone nowhere, but you've taken 50 steps, or however many steps it is. Right, left, whatever. And so that is just, do you recognize that this is the total distance traveled from 0 to 40? And in fact, that's the first answer to the problem, is what does that mean? Well, it means the total distance that she jogged. Now we can estimate it with a right Riemann sum. For subintervals, which makes sense because that's how many, that would be perfect for the table that we have. Trying to get it all on the page at once here. So this would make 4 subintervals. So right Riemann sum just means add the rectangles. What's the width of the first rectangle? The width of the first rectangle. 12. Like that. There we go. So the first rectangle is 12 wide. And how high is that rectangle? Or what height do we want to use? 200, because we're doing a right Riemann sum. So we're going to use all of the right values. So 12 times 200 plus, how wide is the next rectangle? 8. And its height is 240 plus 4 times, what height should we use for this third rectangle? Positive or negative? We're doing the distance, so we want to use the positive. Okay, so she was going backwards, but we don't care about the backwards part. We just want how fast she was going. So 220. And then that last one, the width is 16. And the height is 150. And this is no calculator. And now I definitely want a safe stop, right? I do not want to, I mean, I could, but I don't want to mess with that. Like, let's leave that alone. That's a great safe stop example problem. Using correct units. Okay, so I need units. Oh, well, once we know its distance, that means the unit is meters. And I'm not adding all those up. I don't have time or the interest. I don't want to mess it up. Perfectly good safe stop, one that I'm not even going to continue with. All right, part C. Bob is riding his bicycle along the same path. For 0 to 10, Bob's velocity is measured by that equation. Okay, still meters per minute. Finds Bob's acceleration. We mentioned this earlier. How do I find acceleration? Derivative of velocity. dv dt, or in Bob's case, dB dt. And this is kind of an easy one. 3t squared minus 12t, and that's it. And then at 5, we'll plug in 5. 3 times 5 squared minus 12 times 5. And I don't, again, I'm not evaluating that. I could do it if I want to, but why bother? Let's make sure we answer the question. Bob's riding his bicycle, that equation, minutes, meters per minute, finds Bob's acceleration. It did not specifically ask for units, so I don't have to give it, but meters per minute squared would be the units. Right? Oh, that was pretty straightforward. We know that part D, though, is usually not so straightforward. Based on the model B from part C, find Bob's average velocity. Average velocity. Okay, average velocity is... Well, there's a couple ways to think of this. It's just S of... Oh, he's going 0 to 10. Minus S of 0 over 10 minus 0. The trouble is I don't have an S.
Oh, why is this not like the average value? To like that?
No, that's... So let's use the average value function, or the average value equation, and see what happens. So that would be 1 over 10 minus 0 times the integral from 0 to 10 of v of t dt. Emily, is your question answered now? These are the same thing.
Oh.
Because I had that same issue. I started this problem and I thought, well, this is average velocity, just change in position over change in time.
Okay.
But we don't have change in position, so what's going on here? Well, average value is also this formula, and so we don't know exactly where he is at 10 and 0, but we can figure out how much he's changed from 0 to 10. So 1/10, 0 to 10, of his integral of his velocity. So we integrate velocity, if we integrate velocity, we get change in position. So that would be t to the 4th over 4 minus t cubed.
Why is there a t after?
Oops, I think I was integrating on the fly there. What happened? The 6 divided by 3. I mean, we could have just left it as 6 over 3 and been fine. From 0 to 10, I'm sensing another safe stop in our very near future because I do not want to evaluate all those things. So 1/10, 10 to the 4th over 4 minus 2 times 10 cubed plus 300 times 10. And again, none of those are impossible. Those are all pretty straightforward, but why bother? Like, leave it alone. And then minus, I plug in 0 in all of those, it goes away. So you can leave it. If you want to put in minus and then put all those, you can. But there's my answer. There's his average velocity. I don't have a calculator. Dear grader, you have a calculator. If you want to know the number for that, you help yourself. So I feel like that's not a bad free response problem. The only thing that we hadn't talked about, because we hadn't got to do the Cupid's Shuffle dance, is that difference between displacement and distance. And I think you understand that conceptually, but now we have a formula for total distance traveled versus displacement, which would just be 0 to 40 without the absolute value bars. And so even if you forgot that, you could still get part A, surely part C, and hopefully part D. And I'd have to look up how the points were divided up, but I feel like that was not a hard, in terms of some of the free response questions we see, that one wasn't too bad. Oh, I'm just now getting around to looking at the time. 8:02, 14 minutes, so really it took us less time than that. We took a lot of time explaining and going slow and whatever. So we bought ourselves a couple minutes to spend on a different problem. And a little side note, you can see how good the College Board people are. Like, they covered velocity, displacement, acceleration. They worked in a derivative and an integral. A Riemann sum, a little bit of units work in there. It's like one problem covered a whole bunch of stuff. All right, let's work number 2. This one's with a calculator, so let's see if this one goes any faster. It's 8:03. We get out at 8:15, so we may not have time for this one. We'll see. A tank has a height of 10 feet. The area of the horizontal cross-section of the tank at height h is given by the function a, where a is in square feet. Okay, so this is, as we move up this tank, depending on where we are, there's the area of the cross-section. So if like height is 0 up to 10, at 0 it's a big cross-section. At 2 it's a little less. At 5 it's a little less, and at 10 it's pretty small. So I don't know exactly what this looks like. It's like a flask in chemistry or something, maybe. We don't really know the shape. The function a is continuous and decreases as h increases. Selected values for a are given in the table. This whole worksheet is tables, and so it's almost all Riemann sums. Like if you open the packet and you see a table, you can almost certainly think a Riemann sum is coming somewhere. Part A. Use a left Riemann sum with 3 subintervals. Okay, that makes sense given the data we have. To approximate the volume of the tank. Indicate units of measure. Well, square feet times feet is going to give me feet cubed. Maybe I could even say that to begin with. Volume is going to be in feet cubed. So if that's worth a point, we just got ourselves a point. All right, so volume is going to be the area times the height. So the first width is 2, but we're using a left Riemann sum. So I'll use 50.3. Our next width is 3, and we'll use 14.4, the left-hand side. And the next width is 5. And again, we use the left-hand sum of 6.5. Now, this is a calculator question, so it wouldn't be hard to get an actual answer, but a safe stop is still okay. So if you don't want to take the time to punch things in, leave that alone and move on. Which reason to approximate the value of the tank, indicate units of measure. Okay, so we're done with this one. There's our volume, or our approximate volume. Part B. Does the approximation in Part A overestimate or underestimate the volume of the tank? Explain your reasoning. So Part A, is that an overestimate or an underestimate?
Over.
Uh-oh.
Is it underestimate? Well, because it has a negative relationship.
Maybe look at the picture or look at the data. Like in each rectangle, or in each of these subintervals, we're always using the bigger number. So it's got to be an overestimate. So Part A is an overestimate. Because when we answered a question like this long ago on a test, we need to use calculus words, not just we always use the bigger number. I mean, that's kind of how we know, but so what's a calculus way to say the reason here? Because a left Riemann sum of a decreasing function, I mean, that's our answer, overestimates. Maybe a better picture would have been, I don't know exactly what this looks like, but if we keep using the left-hand value, then we keep getting rectangles that are outside or above the actual graph. A picture won't serve as justification, but it might serve as a justification in your own mind, and then hopefully you could put that in words to get the point for the test. Part C, the area in square feet of the horizontal cross-section is given or is modeled by this function. Based on this model, find the volume of the tank. So I can do the volume of the tank. Well, you tell me, how am I going to find the volume of the tank if this is the cross-section? Kind of helps that we already did the Riemann sum. We want to add up. We want to add up all the cross-sections from 0 to 10. And in fact, that's enough work shown. Now I can go to the calculator. All sorts of mess in here. 50.3 over e to the 0.2x plus x. And I could graph it from 0 to 10, but I don't really care. I want to, if I have time, maybe I go back and look at it, but right now I just want to integrate from 0 to 10 and get 101.325 feet cubed. And if I had extra time, I'd really like to type part A into a calculator and see if they're like in the ballpark. And really see if A is an overestimate of, or over what part C is. But I don't have time for that. Keep rolling. Water is pumped into the tank. Uh-oh. The old part D question here. Water is pumped into the tank. When the height of the water is 5 feet, the height is increasing at a rate of 0.26 feet per minute. So dH dt at t equals 5 is 0.26 feet per minute. I don't know if that's going to matter. I assume it's going to matter. Using the model from part C, find the rate at which the volume of the water is changing with respect to time when the height of the water is 5 feet. Find the units of measure. So find dV dt, but I can tell you right now the units is going to be feet cubed per minute. I really doubt there's a point solely attached to the unit on that one, but if there is, we just got it. So volume would be volume is the cross-sectional area times the height. That's not quite right though, because it was the volume was the integral from 0 to 10. That was our volume. And so if I want, tricky, I need to take the derivative of all that. With respect to time. I wonder if that is right though. The volume. You know what? That's not quite right. That's the total volume. That's the volume of the total thing. I want the volume as a function of height. So I'm going to go up to h. Like that. Because that's a constant number, this first one I wrote. And so if I take a derivative of a constant number, I'm just going to get 0. So I need to know how the volume is changing with respect to height. So now I can take the derivative of both sides. So dv dt. The derivative of an integral, it's just right back to the function. Plug in the top value. But then what else? Chain rule, I need to multiply by the derivative of the top value. And now I see why they gave me this value at 5. I can just plug that in. So now I know the second part. So dv dt at t equals 5 would be f of, I need to know the h at 5. Wait, do I need, no, it's not when t equals 5, it's when h is 5, which is good, because that's the variable I need. So I'm almost there. I plugged that into the calculator. In fact, I already had that in the calculator. Multiply by 0.26, and that's my answer in feet cubed per minute. And I would still have a couple minutes left to type things in and recheck and make sure I was okay on that one. All right, so your assignment is the other two. And again, Wednesday is the multiple choice test. Thursday is the free response test. And then Monday, this worksheet will be due. Topic 4, as well as a video. So, you got 2 problems to do this week. Embrace the climb, enjoy the ride,